Okay, so let's try it this way. As a couple reminders, don't forget the week 7 lesson on the planets is due Sunday night. Don't have a quiz this week, but the deadline for doing the test retake and or redoing or turning in for the first time any of the labs and such from unit 1. So that would be the week 1 tutorial. Um, Big Bang Web Quest, Nuclear Fusion Lab, and I'm blanking on one more. It was in between those. Hubble's Law Lab. Those four, after Tuesday, I will no longer be taking. So if you want to get some points for that, make sure you do that by Tuesday. Also, the test retake. If you want to do that, you shouldn't need to talk to me. You don't need to set up any schedule. Just it's up on the front page. Go do it. Move on. All right, so like I said, today's going to be a little weird, but if you have questions, throw them in chat, as I've probably already said, and can pause this, get those answered, and then get back to it. Shouldn't be a whole lot different because there's not usually a whole lot of talking in chat anyway. All right, so if I go ahead and share the screen. All right, so what we got, we left off on Monday because Wednesday we had the workday due to the SAT. Hopefully everyone who attended that did well. We finished up talking about Venus and specifically the, forgot to start my stopwatch, specifically the possibility of life on Venus. So given that, there have been quite a few missions to Venus, and you should be keeping track of the missions. You know, for example, Mercury, we had Messenger, and we have Bepi Colombo on the way, and then Mariner 10. For Venus, there have been quite a few more, and most of them are very successful. And you'll see, hopefully, in this today, you'll see why that's very important. A lot of them were Russian for whatever reason. We did Mars, and Russia, Soviet Union, I guess at the time, did Venus. They're both about equally easy to get to. Venus is about a 3-month cruise for probes to get to, and Mars is about a 6-month cruise. Venus you can launch from about every year and a half, whereas Mars has a 2-year launch window. What that means, and you'll see it when we get to the Mars missions, is it's like, you know, there's a window that just closed recently, so there were a lot of missions on the way right now because they all had to launch near the end of 2019 and beginning of 2020, and the next window will open up around 2022, and then 2024, and then 2026. So you got to be prepared for these launch windows. Essentially, what the launch windows mean is that it's the most efficient way to get there. To launch any other time, you need a whole lot more fuel, which makes the mission more complicated and more expensive and less likely to succeed in the first place. A lot of them were orbiters, especially the United States ones. We got Magellan and then Venus Express from the European Space Agency. There is a JAXA mission that actually is still holding on. They're still holding out hope to actually get that thing running again. But there have been 9 different landers, and I love this one because we talked about the high pressures and all that. Like the camera covers, to make these cameras last as long as possible, had to be made of transparent diamond, which is just crazy. And so most of these, Varena 9 through 13, and then Vega 1 and 2, were landers by the USSR, the Soviet Union. Pioneer was one of the earlier probes that we launched. It's not actually a lander. Pioneer was an orbiter, but it's listed as a mission on the surface because when it was time to end the mission, we tend to crash the probes. So the reason is what's called planetary protection. Basically, if there is a chance of someplace in well, at the time it was we were hoping that we were going to, fill up the solar system with traffic, and we didn't want a loose probe, smacking into somebody like a deer on the highway. But nowadays we do it like, the Cassini mission to Saturn was purposely deorbited into Saturn because there are some moons that might hold life around Saturn, and we don't want to crash a probe from Earth with all of our microbes on one of these planets. Because if we go there and find microbes, now we've got to figure out, did they come from us or did they develop there? And that's a very important question we would like to answer. So usually at the end of their mission, we crash them into something so they're not just littering up space, even though outside of Earth orbit, space is pretty empty. So Pioneer, we crashed into the surface of Venus and we went, well, let's see what data we can collect on the way down. And its atmosphere was so thick, it actually survived all the way down to the surface. It was a gentle enough descent that landed all the way onto the surface and kept transmitting for a couple of minutes before it fried. So technically, it's a landed mission. All right, let's talk about the moon. We're not going to talk much about the Earth because if you want to take the Earth, talk about the Earth and the geology of the Earth and volcanoes on the Earth and the atmosphere of the Earth, well, maybe you should have taken environmental science, but you didn't. You took astronomy. So let's talk about the moon. What I got here is a topographical map of the moon. So near side, far side. We watched in that video, and hopefully you know this already. The moon is tidally locked to the Earth. What that means is the orbital period, the time it takes the moon to orbit its celestial object, in this case the Earth, is exactly the same as its rotational period. What that means is you will always see the same side of the moon. Because when the moon's over here, let me see if I can grab an actual, like, do I have a ball or something? Because that'd be useful. It's a good thing in these pre-recorded videos, I still haven't planned anything out. Whatever, I'll take my water bottle. Okay, so if this is the near side of the moon, right? If this didn't rotate at all, then as it moved around, let me try and get this in here. As this moves around, well, this isn't facing me anymore. It's going that way. But because the orbital rotation is exactly the same, as it orbits around, it rotates to keep the same face towards me. That is tidal locking. So the reason we have the near side and far side of the moon, or the near side and the dark side of the moon, is simply because of this tidal locking. Now, the dark side of the moon is a misnomer. It is a misleading name. The dark side of the moon is brightly lit the exact same amount as the far side of the, or the near side of the moon. The difference is when the dark side of the moon is lit, that's a new moon. That's when you don't see the moon in the night sky because it's up during our day. So it's just, we call it the dark side because whenever we can see the moon easily, the far side is in darkness. Now, notice some of the differences here. Notice that we've got on the near side of the moon, we have these large areas here in blue, what we call seas or Mariana. So the Sea of Tranquility where Apollo 11 landed. These are from a couple different things. These are from, can be some impact craters. It can be lava flows from when the moon was geologically active. But it's also the fact that there just aren't as many collisions on the moon as there are on the near side of the moon as there are on the far side, because to get to the near side of the moon, you generally have to hit the Earth first. The far side is the one that's taking the brunt of the impacts, and that's why the far side is as cratery as it is, because it's constantly getting pummeled. All right, so what do we know? The only natural satellite of the Earth. Now, this is a little controversial in some circles, but technically, the word moon only refers to our moon. So, for example, to talk about the moons of Jupiter is technically incorrect because, well, a moon refers to our moon. The scientific term is a natural satellite. They used to just be called satellites, but then we started launching artificial satellites, which we now just call satellites. It's a very confusing terminology. So technically, any object orbiting another planet is a satellite, which we simplify to, or we break up into artificial and natural satellites. So artificial satellites would be communication satellites and GPS and in internet and radar and climate monitoring and reconnaissance and all sorts of stuff. Space shuttles, the International Space Station is a artificial satellite. Natural satellites would be asteroids and moons and things like that. But once we started getting a whole lot of artificial satellites, everyone just started calling those satellites. So the terminology of talking about moons of Jupiter was already there, and it became much more acceptable. So even in scientific circles, you don't see a lot of debate about whether it's a natural satellite or a moon. They basically just mean the same thing. But if you ever run into somebody who's incredibly full of themselves that tries going, pulling the full nerd, technically, just tell them to shut the hell up. It's a moon. All right. It was once geologically active. It still has a core to a degree, and we actually know quite a bit about the moon for a wide variety of reasons that we'll get to here in a little bit. And it is very similar to the Earth, suspiciously similar to the Earth in many ways. So it still has the inner core, outer core, and mantle, the same thing you see on the Earth. So on the Earth, we refer to the inner core as that ball of ironish metal in the center that is surrounded by a large flowing sea of liquid magma. Because keep in mind, magma, liquid rock inside the Earth, magma, liquid rock outside of a volcano, lava. And that spirals around the inner core, and that's what creates that magnetic field. And then you have a bunch of layer of rock, we call that the mantle. And then the very outer layer, basically the only part of the Earth we've actually been on or near is the crust. And the moon has all those same things. Doesn't have much of a crust. It's mostly all mantle, just because it doesn't have the atmosphere for oxidation and stuff like that. Um, it's just a lot smaller than the Earth. That's it. And because it's a lot smaller, it cools down faster. So we talked about ways of getting rid of heat, and we talked about conduction and convection a little bit, and this concept of radiation, that everything based on its temperature radiates heat away in the form of infrared light. So the larger the object, the more infrared light that it emits. So you would think that the Earth would emit more because it is larger. However, a sphere is a special shape. You might remember from geometry that a sphere is the most volume you can get in a three-dimensional object with the smallest surface area. So cubic meter for cubic meter, a sphere gives you the least surface area possible. So even though the Earth is larger surface area radiates heat out faster, it also has a lot more heat inside of it. So the Earth cools slower. So the moon has cooled faster than the Earth has, and the end result is that the core of the moon is mostly dead. It no longer has an active magnetic field. We know it did, because we've brought rocks back from the moon and we've looked at magnetic fields in the moon, and they indicate that at the time the moon was still geologically active, there were still lava flows and all that, and those rocks were formed. They locked in the magnetic field that appeared at the time. So there's still a very weak magnetic field because of those rocks, but the core is no longer as active as it once was. Doesn't mean it's completely solid all the way through. It's not an ice ball. It's not a frozen planet, but it's just not very active. So there's not a whole lot of there are moonquakes, but they're very different and actually mostly due to meteors impacting the far side of the moon, things like that. It doesn't have any atmosphere. Now, I said except at night because it's this really cool thing that the moon does. So the moon is covered in rock and what's called regolith. Now, regolith is what on Earth you would call dirt, but it means something very different. So, dirt on Earth, you get some nice potting soil, some good dirt. It's soft, it's gentle. You can pick it up and you move it out of your hands and it just drifts down. It's very, very nice stuff. And the reason that happens is due to a bunch of different processes. So, water flowing through a rock is going to erode away at that, right? And air and wind, and it's going to tumble dirt particles against each other, and that's going to wear away, right? Think of in manufacturing, if you've ever watched How It's Made or any of those shows, whenever they manufacture something to take away a lot of the sharp edges, they'll like throw it in a big tumbler with rocks in it, and that smooths it all out. The moon doesn't have an atmosphere. It doesn't have water, at least not flowing water. It does have some water in its poles. It does have some water in the deeper part of the craters that have formed where a comet impacted and left some of its water behind and instantly froze. Um, but it doesn't have these things that erode away at it and soften it. So moon dust is nasty. The spacesuits the Apollo astronauts wore had to actually have layers of Kevlar in it to protect the spacesuits from getting cut apart by the moon dust that they were going through. Most of the astronauts who landed on the moon and took these trips have unfortunately passed away due to cancer. Not all of them, but many, for a couple reasons. They had a deeper space away from the Earth's magnetic field. They were exposed to more radiation, but also the ones who landed. There's a concern of breathing this stuff in could be even worse than asbestos, essentially, which is a concern if we ever want to have a long-term colonization of the moon or a long-term base on the moon. Is how do you decontaminate these suits, and how do you get them clean of this regolith that sticks everywhere, and it's electrostatically charged, and it is just it'll cause cancer, it'll rip things apart, it'll stain everything it touches. Regolith is some nasty stuff. But the reason I bring up except at night is this really cool thing happens. So if you were on the moon and it's been nighttime, or it's been daytime, and you're just passing into twilight, what can happen is the magnetic field of the sun you're passing through, the combination of the electric field of the sun and the moon, sun and the earth, because this regolith is so light comparatively, and it's so well at holding electric charge, you can actually get an atmosphere of dust. Where the magnetic field comes in, electrically charges it, and then the dust is repelled by the surface of the moon. And because gravity is so weak, you can get this. I think it's been caught on camera once, but it's kind of this very reflective, almost twilight of a dust atmosphere. It's kind of a cool thing. Now, here's what I said about it is suspiciously similar to the Earth. Well, actually, one more thing, wonky gravity. Because the moon is smaller, it's not fully differentiated. And because it's got so many impacts, there are some places where there's a bunch of impacts which were iron asteroids. And there's some places that were icy comets. And so the places that are iron asteroids are a whole lot denser, not less dense, a lot denser than the comety areas. So having things orbiting the moon is tricky because the gravity isn't nice and uniform. Like a satellite will be flying over and then suddenly start getting pulled down, and all of a sudden it's got to burn some fuel to reestablish orbit. Now, luckily we've mapped the gravitational field of the moon, so we kind of know what's going on now. But sometimes some crazy stuff can happen with some satellites. All right, so made of the Earth. So where did the Earth or the moon come from? Oh, really quick. I said there is water, but no liquid water. Here's why. If you don't have an atmosphere, you cannot have liquid water. So we're not going to watch all of this, but we are going to watch a bit. So what this is a beaker of water with a thermometer in it that has been placed in a vacuum chamber. And they're going to slowly pump all of the air out of this. Now, I believe I've got the sound off because it's ridiculously loud. So if, okay. Let's try that again. Here, let's turn the sound on. What's worse that happens? Oh, they haven't even turned it on yet. Wow, I just realized I did not switch over computer sound. So all that narration I was letting happen served no purpose. Look, the point is the less the atmosphere, so water molecules are constantly in motion, and the lower, when a water molecule tries to escape the surface, basically air molecules are there to slap it back down and tell it to get its ass back in the water. But as those air molecules go away because atmospheric pressure is dropping, those water molecules can escape. And at a certain point, water spontaneously boils. Liquid water cannot exist on the moon because as soon as if you took a bottle of water and dumped it out on the moon, it's not like in sci-fi movies where like something instantly turns to ice. Like I think I saw one really crappy like 2 a.m. B-roll sci-fi like actors that have been out of work for a decade, where like someone was out in space in a spacesuit and they had a water bottle and they like, uncapped it and like shoved the water bottle at them, and the water came out and instantly froze into like an ice spear that's No, it takes a long time for water to freeze. What it would do is spontaneously boil away. And this is why, if you've ever seen any people who fly like the U-2 or the former SR-71 airplanes that fly really, really high, they wear what looks like a spacesuit, because if they were to eject at the very, very high altitudes that they fly in just a normal, like, G suit and helmet, and their face is open to it, as soon as they popped out of that pressurized canopy, the water in their eyes and their tongue would all start to spontaneously boil, and the nasal passages, and it would not be a pleasant thing. So at a certain pressure, liquid water cannot sustain itself, and the moon being in a vacuum cannot have liquid water. Same deal with Mercury, same deal with Mars. Mars does have an atmosphere, but it's much too low to allow for liquid water. All right, so how did the moon form? Well, remember what I said is, in the early solar system, it was all these rocks and what we call protoplanets. Like, basically think really big asteroids, things trying to form planets, all smashing into each other. It's all very chaotic. And as they're smashing into each other, what they wind up doing is, well, grouping together and having more gravity and pulling more stuff in. But the Earth is a ball of liquid rock at this point, because, think of, if you've seen any movie that has a meteor impact, like, I mean, these are all older, but Evolution, Men in Black, something like that, they always depict like some big collision as like having smoking ground around it, because in physics you learned about conservation of energy. These things have enormous amounts of kinetic energy, and that enormous amount of kinetic energy translates into an enormous amount of heat. So the Earth is a ball of liquid rock, and what happens is another protoplanet, so we think it was about the size of Mars, we've named it Theseus, slammed into the Earth, ripped part of the Earth off, destroyed itself in the process, and this debris of the Earth and Theseus kind of starts coalescing, forms a ring around the Earth, which eventually coalesces or gravitationally attracts itself into the moon. So I'll play this quick little simulation. So what we have here is at the very, very start, we have the Earth here, and then this would be the smaller planet Theseus out there. Now notice the surface is blue. You're going to see the darker colors for the cores, and notice all the mixing that's going on, right? The Earth is not solid at this point. It's just essentially a ball of liquid rock. And so all this stuff starts mixing, stuff spraying everywhere. This is a collision that would take hundreds of years for everything to play out. And you notice this kind of ring system. Some of this debris that has been shed from the Earth coalesces into a set of rings, much like Saturn does, or actually Jupiter, Uranus, and Neptune do as well. Well, the Earth is not actually large enough to sustain a ring system. That will always either get pulled back into the Earth or do something else. And so the end result is you get a lot of that material slowly pulled that back down into the Earth, and you get a lot that kind of pulls itself together gravitationally and forms the moon. Now, how do we know this? So there's a couple of different options. Off the top of my head, I can think of, there's four. There's four main options for how the moon was formed. So I'm going to give you what they are, and then the main reasons why they couldn't have happened until we get to the giant impact theory, is what it's called. So the first is the Earth and Moon just happened to form together. The problem with that one is the moon, while still pretty far away from the Earth, is close enough, and the Earth is so much bigger, we would have pulled material from the moon. The moon would have to be almost double the distance away that it is to have been able to form separately from the Earth. And the problem with that is that could work if the moon were getting closer to the Earth, but the moon is actually escaping the Earth. Every year the Earth spins a little slower and the moon moves a little further away. So that one doesn't work out. There was the fission hypothesis, which was at some point the Earth was spinning so fast it flung part of itself out into space, and that material is what caused the moon. The problem is we've run the math on that since that idea back in the early 60s, and computers got better, and we could run the fluid dynamics simulations for that. And fluid dynamics take a crap load of computer power, which is why we couldn't really run it till the 80s and 90s. And the end result is, for the Earth to do that, it would have to be spinning fast enough that it would have just flown apart and would have never formed the Earth. So that one's out. There was the capture hypothesis, which is the moon formed someplace else, and it got captured by the Earth's gravity. The problem is, again, the moon is smaller than the Earth, significantly so. But by moon standards, it's very large. There's only 2 moons I can think of off the top of my head that are bigger than the moon. And the Earth, for all of its relative size, um, for captured moons, we talk about like asteroids around Jupiter, essentially. For a while, we thought Phobos and Deimos around Mars were captured moons. It doesn't really work for the Earth. So now we have this giant impact hypothesis, and some of the support for that is in this hypothesis, you would have Theseus and the Earth mixing, right? Because every planet has its own unique chemical signature, because the closer into the sun, the more likely you are to get certain elements, and the further out, the more likely you are to get other elements, and in the middle, you get different compositions. And the composition of the moon and the composition of the Earth, because we've tested it, because we've been there and brought moon back to Earth to test, is the same. The Earth and the moon are made of literally the same material. So the impact hypothesis would involve this material mixing together, and essentially what is the Earth would be what the Earth originally was plus material of Theseus mixing in. And that does explain some other things on Earth, why there's certain chemical compositions like we would expect to be between Venus and Mars, and we kind of got a little bit of a mix of everything from this giant impact. All right, quick little video tour of the moon. We'll finish up with the moon and at least get into Mars before we finish up for today.
Mic off.
To nearly everyone, the moon appears to be a sterile, gray, unchanging world. But while the moon has remained largely unchanged during human history, our own understanding of it has evolved dramatically. Thanks to new observations, we now have not only unprecedented views of its surface, but a whole new tour of the moon that shows how both it and other rocky planets in our solar system have been shaped over billions of years. We'll start with one of the largest impacts, Oriental Basin, a feature that's as wide as the distance from New York City to Cincinnati. Using new elevation measurements, we can clearly see the effects of what is likely the last giant impact event in lunar history, with its outer mountain rings rising many kilometers above the lowest points inside the crater. The interiors of some craters in the moon's polar regions, like Shackleton, haven't seen sunlight in over 2 billion years. However, new measurements have created our best yet maps of these types of craters, allowing us to see deep into the shadows of this surprisingly young-looking impact crater in the south that's more than twice as deep as the Grand Canyon. Some impacts are invisible for other reasons. Although the ancient South Pole Aitken Basin is difficult to see from orbit because it is so large, new LRO topography maps reveal the largest impact basin in the Earth-Moon system, measuring several kilometers in depth and around 2,500 kilometers in diameter. Only the Hellas Basin on Mars rivals it in size. One of the youngest large-scale impacts on the Moon is the Tycho crater. This fresh crater may have formed only 108 million years ago, when dinosaurs roamed the Earth. We now also have an extreme close-up view of the crater's central peak, revealing a mountain with sharp edges, building-sized rocks, and a central boulder about the size of a baseball stadium. The Aristarchus Plateau is another recent lunar formation that has long interested scientists and astronomers. The crater itself formed in the same era as the Tycho crater, and what appear to be snaking river valleys were actually carved by ancient lava flows. Next, we arrive at Mare Serenitatis on the near side of the Moon. In December of 1972, the crew of Apollo 17 landed in the Taurus Littrow Valley, marking the last time humans have visited the surface of the Moon. With images from LRO's narrow-angle camera, we can clearly see the evidence of that visit. In this image, you can easily see the base of the lunar lander, along with the lunar rover, parked far from the blastoff zone. You can also clearly see the astronaut trails and the wheel tracks left on the lunar surface. We now head to the far side of the Moon, which cannot be seen from Earth. Our first stop is the Compton-Belkovich region, which shows evidence for young volcanic activity in the far side highlands. This feature is unique not only because it is isolated from other volcanoes in the area, but also because it is located nowhere near the Maria, where volcanoes are usually found. Also, on the far side, we find the Jackson crater, which, like the Tycho crater on the near side, has an extensive and complex ray system. In fact, this crater is often considered to be like a twin to Tycho. Finally, the Tsiolkovsky crater stands out as an excellent example of a far-side crater filled with a sea of ancient lava, known as a mare. It is particularly interesting to scientists and other observers because of its isolation from other similar craters, as well as its beautiful central peak. As we continue to study the Moon, our understanding of it improves, giving us new insights not only into how it has evolved over time, but also how other rocky planets in our solar system have come to look the way they do. With new missions, new instruments, and new technologies, we will continue to improve our knowledge of the Moon and better understand the history of our solar system.
Mic
All right,
on.
just to give you a little idea, Google Maps actually does have Google Moon, and you can do Street View on the Moon if that's something you really want to do. All right, so yeah, definitely not gonna get to Mars today, but that's okay. We know a lot about the Moon because we've been there, because it's so close to us. It lets us talk a lot about it. All right, very briefly on phases of the Moon. You should have gotten a lot of this in middle school. If it does turn out there's confusion about it, I'll come back to it later. But essentially, we get the phases of the Moon. So the new Moon is when the Moon is on the day side of the Earth. So that's when you can actually look up at 4 o'clock in the afternoon and still see the Moon there. So there's no Moon at night, but the Moon is visible in the day. We call it a new Moon because it looks like it's in shadow. Because remember, the Moon doesn't glow. The Moon reflects light from the sun back to the Earth. It's it's got a very high what's called albedo, how much it reflects light. So when it's on the day side of the Earth, you see it during the day, and because the sunlight is hitting the dark side of the Moon, the far side of the Moon, it doesn't reflect light back to the Earth, and we see it as a dark shadow. And then as it starts moving further and further from the day side of the Moon, you see it in these crescent shapes. So the waxing crescent, first quarter, waxing gibbous. You don't have to know all these names, but you should get the idea. And then the full moon is when it is fully on the night side, and that is when you can see the entire thing. It's reflecting light back, all of this stuff. All right, so some features about the Moon you should know about. So you've got basically, it's broken up into two parts. You've got what's called the highlands, which are mountainous and cratery and all of that. And then you have the Mara, which are the lowlands. They are basically lava flow. They're very surface. So they're called Maria, or the singular is Mare. And they're lava flows from old volcanoes long since dead, but forming what they call seas because they looked like flat oceans back in the day. And for example, Mare Tranquillus, the Sea of Tranquility down here is where Apollo 11 landed. All right, so missions. There have been so many missions to the Moon. Satellites, landers, rovers, people. It's the only place other than Earth and we've ever been in the universe. So originally it was the United States, the USSR. So early in the space race, Russia was kicking our butt. They were the first ones to land something on Mars. They were the first ones to land something on the Moon. Just before the US was set to land people on the Moon, they dropped a rover and dropped little USSR pendants all over the Moon because they could, and it was the Cold War and weird crap happened. 1990, Japan was the third country other than the US and USSR slash Russia to have landed. European Space Agency has landed one, and then just recently, about 5-6 years ago, China landed their first rover on the Moon, named what is it? I believe it's Chang'e. Named after the moon goddess and the rabbit that live on the moon in Chinese mythology. So there have been 6 crewed missions that specifically went and landed on the Moon. 5 that landed on the Moon, 11, 12, 14, 15, and 17 landed on the Moon. Apollo 13, if you don't know what happened there, watch the Tom Hanks movie. It is one of the best space movies that has ever been made. It is fantastic. Great movie. Fairly accurate to reality. There's only like 4 or 5 little nitpicks I could make on that movie. There were an additional couple of missions that orbited the moon. Apollo 8, no, sorry, Apollo 9 was the first one that actually, no, it was Apollo 8, sorry. Apollo 8 was the first one that actually orbited the moon. So they went on what's called a free return trajectory. So they launched away from the Earth, they looped themselves around the moon and came right back. And let me pull this up really quick because it's that was the mission that gave us a very famous picture taken by, well, actually, it's in dispute exactly who took it. But it's a picture called Earthrise. Here it is right there, taken on the Apollo 8 by the Apollo 8 spacecraft of the Earth coming up over the horizon of the moon. This mission was also well known for it took place over Christmas Eve. And was considered the end of one of the capstones for the year 1968, which was a tumultuous year. If you know anything about it, there was the JFK assassination, the Martin Luther King assassination, all sorts of civil rights unrest. You had protests over Vietnam, all this crazy kind of stuff. And Apollo 8, at the time, in certain circles, there's a whole elements of racism and all this stuff as well, was seen as a unifying moment. And then on the flip side, you have the very famous poem Whitey on the Moon. So it's a complex issue. All right. Then you got, so you had the landings, all that kind of stuff. Currently, I didn't actually update this slide, but NASA is currently planning on something called Project Artemis, using the new, maybe launched next year, SLS or Space Launch System. The plan would be to launch a capsule and a reusable lander, possibly with a orbit out what's called L2. It's out past the moon where the Earth and the moon's gravity cancel out. So it's very stable orbit and doesn't require a lot of fuel for boost, which is good because it would be abandoned for years at a time. But they're trying to run Project Artemis. Artemis, if you don't know your Greek mythology, being the sister of Apollo, who is the one who pulled the sun around in the chariot. Artemis was the goddess of the moon and the hunt and all sorts of stuff. All right, and that is it for the moon missions. We will get more into detail in this when we talk about human spaceflight in, probably at the end of the semester. Now, at this point, I will just end this because we are going to get to Mars next, and by this point, it looks like I've been talking for nearly 40 minutes. So just to wrap up, don't forget the week 7 lesson. That's the only real thing due. Otherwise, make up your work. I will also tell you that Thursday night, the board did vote to accept the administration's proposal for Q2, which for us doesn't change a whole lot. There's going to be a communication going out to you guys on Monday. The only thing it changes is classes become 5 minutes longer and the transition, the passing periods become 5 minutes shorter. So 10 minutes between classes instead of 15. There are some people going back to the building, but that is a very small group, usually for very, very specific reasons. So for us, we're going to do our entire semester together online. So if you've got suggestions, if there's anything I can do to help you out with finishing up the year like this, please don't hesitate to let me know. On Tuesday and Wednesday, or Wednesday and Thursday more likely, we're going to be getting 2 of the 3 projects we're going to do for the semester. So one is going to involve you making some kind of presentation, we'll get into the details of it, about a planet or celestial object in the solar system. So Pluto would count, Ceres, Vesta, some of the bigger asteroids, lots of stuff. So think about what in the solar system you might be interested in. That's a more short-term project. And then there's a longer-term project. So we're going to do 2 short-term projects and a long-term project for the semester. And we'll get you those details on Wednesday and Thursday. All right, probably this video is long enough. So as long as we didn't have questions, I will see you. Enjoy your weekend, and I'll see you on Monday. Thanks, everyone.